Hi, David.
Hello.
Hi, guys.
Hi, David.
We're coming 1 minute.
We have New York, but New York is empty.
I mean, there's nobody in New York.
Yeah. Where are you, David?
I'm in Exeter in the UK.
Uh-huh.
Can you hear me?
Wow. You should have joined us here.
He's one step forward.
I know. I was supposed to, but I got 2 meetings that hit in the same week.
Okay.
I also
Some of us are in New York, David.
I also work on planets, and we at Flatiron we're part of the Terra hunting experiment, which is headquartered in the UK, and it's the annual science meeting.
Okay.
Partly David's fault that I'm here. Oh wait, there's too many Davids. That's not really a specific thing to say.
Too many Davids.
Yeah, I thought we would not use the name David, given the composition of the panel,
I
and
go
just
as
use our
Hogg,
last
so I'm
names.
good.
So I'll just go by
Hogg rules.
Spergel, Hogg, Spergel, Weinberg. Otherwise,
Okay, good.
it's
It's
just too
Spergel's
confusing.
fault that I'm here.
Yeah.
Good.
Where's my water? Sorry.
Okay, I suppose that David Spergel, you're the main here.
Shall we start now, or
You
are we-
decide whenever you're ready. We are ready here.
Yeah.
Sorry,
We're waiting for people to assemble here. They're being. Okay. Paco is going to crack the whip. Everyone's out, I think, drinking coffee or something.
No, don't tell them. Or at least don't give it to Henry.
We should send you our bell, which is very effective to gathering people and filling in the amphitheater here.
All right, we're just going to start talking, and that will encourage people to come in even faster. So we want to begin this session with a dream, and it's a dream that I suspect I may be the only person in the audience that I think I was there when it was evoked, and if not, it's one of these events where I'm not actually sure if I was there or if I heard the story often enough that I believed I was there. So I'm going to turn to David to talk about a dream. Weinberg, yes. Weinberg, to evoke a dream envisioned by one of the senior leaders of our field 40 years ago, which in a sense I think connects very much to where we might be in machine learning. So David, Weinberg.
Yes, indeed. So, I started graduate school in the mid-1980s when, cosmological simulations were just coming to the fore. So we had, high-resolution simulations with 32 cubed particles, and particle mesh simulations were getting to 128 cubed particles. And, hydro simulations, cosmological hydro simulations didn't exist yet, but they were sort of on the horizon. So it was clear that this field was going to grow, but I think even if you understood Moore's law, I would have found it hard to anticipate in 1985 just how strong our cosmological simulations would be today. And I do, as David said, think that we're in a kind of parallel position with machine learning now, and so I thought it would be useful to kind of go back to this summary from the Milky Way IAU symposium in 1983. David might have been there. I wasn't, but I read it. So when Jerry Oestreicher gets to the subject of spiral structure, he has some remarks and he says, somewhat depressed, I went home for an early nap in which I dreamt that I was blessed with an army of graduate students, each one more eager, intelligent, and industrious than the last. Then with this army and unlimited access to computer time, all the relevant physics was put into the computer model. It took a year to get the bugs out, but then when the first run was complete, voila, outcome pictures representing at every wavelength, real spiral galaxies. By suitable adjustment of knobs, every type of galaxy can be made. What a happy dream. Success, perfect understanding of the phenomena, peace and understanding will reign. And he then goes on, say, with this great simulation, he wasn't, knew there was a lot in it, so he showed it to the observers, who argued about whether it was, in fact, a one-arm leading spiral or a two-arm trailing spiral. He went to the theorists, who each argued persuasively why their particular piece of physics was the crucial one, and all the other ones didn't really matter. The dream ends in chaos with cries and shouts, grown men fighting over control of overhead projectors, etc. So I actually think this little "I Have a Dream" speech encapsulates, quite a lot of nice things about how we want to use numerical simulations. And so, as I was thinking about this debate, I too had a dream, and I think it seems from listening to Rupert Croft's talk and the exchange afterward on Monday that Rupert and Douglas Scott had pretty much the same dream. So in this dream, all the Bitcoin miners realize the error of their ways, and they take all of these facilities that have been devoted to Bitcoin mining, and they decide it should just all be turned over to the astrophysicists. And so over the course of several years, they're divided into two sets. One set runs the most powerful computer hydrodynamic radiation transfer simulations, and the other set takes the output of those and trains the most advanced machine learning model on those simulations. And then, all of these things are sort of brought together in a computer that, of course, we refer to as deep thought. And over the course of about a year, deep thought is fed with all of the data from Euclid, from Rubin, from Roman, from the Chinese Space Station telescope, DESI 4, Simon's Observatory 6, etc. And, the philosophy is whole hog, so to speak. And so instead of giving, galaxy positions and maps on the sky, it's pixel level, time ordered data, etc. All of this is fed in, and then for 6 months, deep thought grinds away and then finally says it's ready to give the answer. So huge press conference with all of the assembled cosmologists excitedly there, and deep thought says W is minus 1.058 plus or minus 0.004. So that's about a 15 sigma rejection of standard cosmology. And there is, celebration at this fantastically exciting discovery. And of course, there are values for all the other cosmological parameters, but they're actually not very interesting. They're within standard expectations. But this one is the surprise. So of course, the cosmologists ask deep thought, well, can you, summarize what leads to this result? And deep thought, thinks for a microsecond, and then in politeness to the humans, kind of delays for a couple of seconds, and then says, tricky. It's a very high dimensional parameter space and a very large number of constraints. So there is no simplifying projection that conveys the result. So the cosmologists are a little unhappy. They ask, well, are there summary statistics that you could show that would at least illustrate the conflict that arises with standard cosmology? And deep thought thinks for another microsecond, response, no. And so then the cosmologist asks, well, what if we drop out, this data set or that data set or these scales? And deep thought, explains that each individual piece that you drop out weakens the result a little bit, but there's no one decisive piece. There's no subset of the things that it's coming from, and then asked to show anything that would kind of illustrate the conflict in some little piece. Just explains that if you force lambda CDM, then any individual statistic you would come up with is fine, but just the overall chi-squared, although of course it's all simulation-based inference, so it's not as simple as chi-squared, but basically the overall chi-squared is just very bad, and that's the way it is. So at this point, a quarter of the community goes on to writing papers explaining how W is minus 1.058, and the rest turns their attention to interstellar dust. So, things that I take from this parable, but I think, others will take different things. I think, machine learning methods are great when you don't need the answer to be accurate. And an example application there is when we talk about making mock catalogs where we want to calculate covariance matrices, but we don't care so much about the individual answers. So machine learning accelerated simulations are fantastic for that. They're also great when you can check the answer, either by experiment or by full calculation. So, I think, again, machine learning accelerated simulations where you can then go back and do the full simulation in the region of parameter space you care most about. That's a great application in cosmology. I think, the reason that protein folding has been the single biggest success is that that's a place where we don't actually care how machine learning got the answer, because you can predict the properties of the protein and then you can do an experiment and find out if it's right or not. I'm not sure we have the analog in cosmology, but if we did, that's a case where this is great. Something where you can understand the answer and reproduce it in some other way. I actually think it's terrific if we can take these machine learning methods and end up with something that we can put into summary statistics language. I think the wavelet transform stuff that Brice Menard talked about in his opening talk is a very nice example of that. And of course, best of all, if you actually learn new physics from the answer itself. I think there was a lot of discussion about in yesterday's debate about latent space. I think one of the nicest examples I've seen of this so far in the astronomical literature has been the Cranmer et al. Paper on instability of planetary systems, showing that you could predict what was happening after 1 million years based on the first 10,000 years, and so you really could go back and see what it was in that very early behavior that predicted instability of the systems. I think that's a lovely example within astrophysics. I haven't seen an analogous thing within cosmology yet, but maybe we'll get there. Okay, so that's my parable.
Thank you for that inspiring parable. Now I want to turn to the panel and ask them, all right, we'll start with that parallel and even generalize it. You are a referee on either that paper or a paper claiming a surprising result based on machine learning in other areas of astrophysics, whether it's planetary exoplanets or galaxy formation. And it's a result that contradicts, that we really learned something from, that it's not confirming existing prejudice. And I want to ask each of the panelists to think about what are the questions and the tests that you as a referee want to ask the authors so that the paper is acceptable. I think of different levels of proof. There's things that are viewed as true proofs by mathematicians. That's sort of a high level. The next level, those that are believed by physicists. And then those believed by astronomers. And, in a sense, it's this question, has machine learning even reached the level to convince astronomers? Though before doing that, I couldn't help but respond to David Weinberg's statement about going and often working on interstellar medium. My experience with surprising results in cosmology It's probably dust. And Hogg knows what I'm talking about.
I do.
So I'll start with you, David, and then we'll turn to Nabila, and then Helena, and then back to David Weinberg.
I'm actually going to share some slides if that's okay. Let's see, does this work? Oh, of course, I've hidden my thing. I assume people can see those slides?
You're visible here in New York, and I assume in Paris as well.
What about the slides? Yeah, the slides
Perfect.
are good. Okay, good. So
The slides are good.
I just pulled up a couple of slides from a talk I gave recently at I think it was at SUNY Albany, but I just wanted to lay out some philosophical things, and it's going to sound like I'm in violent agreement with Weinberg, but I think I'm not. I'm going to try and pull an example where I'm not, because I think the panel is probably more interesting if we don't agree. But one of the things the thing that I think is, for me, the thing that makes something a machine learning method is that it has these kind of two philosophical things behind it. One is that there's only data. So a machine learning method takes in data as training, and it works on data at the test step, and it's finding relationships between data and data. And that means that the latent structure is irrelevant. And I want to just remind everyone in the room, I think everyone in the rooms are very aware of the point that physics is all about latent structure. We actually, everything we debate is latent structure. W, which David brought up, is a latent property of the universe, not the data. And all of our interest and all of our focus is on the latent structure, which is exactly what doesn't matter to machine learning. And the second thing I would say is that there's an epistemological understanding in machine learning that if your method works well on held out data, then it's correct. And once again, I would say that is very, very strongly at odds with what we believe as physicists. We don't think that general relativity is good because it works on held out data. We think that general relativity is good because it has all sorts of important and essential properties that we think are essential to physics, like that it's a gauge theory and that it's coordinate free and things like that. So one point of view that I have, this is not quite answering David's or Spergel's question, but it's very, very relevant, is that I think that fundamentally, but it's very relevant to Weinberg's parable, is that fundamentally you can never know what a machine learning method is doing. Now, it's controversial. There's lots of people working on interpretability and interpretable machine learning, but basically I consider that area to be a failure at present. I do think there might be approaches that involve like doing experiments on machine learning methods, but it's certainly not the case that the latent structure of the model is interpretable. And in fact, I think it's deep. The reason it's deep, it's not an accident. It's that we want immense flexibility. And when you have immense flexibility, you're giving up on structure. And so the question from my perspective is, where in science can you use a model that you don't understand and you don't trust? And Weinberg gave an answer that I disagree with, but I will try. So I think one thing that Weinberg said that I agree with very much is that it's great in AlphaFold that you can predict protein foldings, because if you find an interesting protein folding, that leads to experimental questions that you can then follow up. I agree with that completely. But when it comes to the cosmological example, I don't think you can use the machine learning methods in that place. There are other places in the program you might be able to use them. There's lots of places you might want to use machine learning, but you don't want to use machine learning at the high level. And the reason fundamentally is confirmation bias. And there's too many words on this slide, but basically Weinberg was saying, well, it's fine if you can check it. But I actually don't agree with that, because the motivation to check is very strongly dependent on the surprisingness of the results. And the checking by construction is expensive. If checking was cheap, we would never be using machine learning in the system at all. We're using the machine learning because the full simulations are expensive. Then if checking becomes very expensive, we're only going to do it when the result is surprising. And that is almost exactly the description of confirmation bias. So we really are setting ourselves up. And we are cosmologists, so we work in a place where you don't get to try other universes. You don't get to do experiments in the lab. So confirmation bias is very much a problem for us. I'm going to stop sharing. But anyway, so my answer is to Spergel's question is fundamentally, I doubt I could be convinced as a referee, because if the result is whether the result is surprising or not, I'm not going to believe that a precise measurement of W coming from something where uninterpretable models are in the mix.
So basically, you will reject any machine learning paper in cosmology. Hogg?
Was what have we learned from machine learning? And Brice Menard, said very kind of specifically that machine learning hasn't produced much in the way of new understandings in astrophysics, and I agree with that completely. But I do think machine learning has been very, very important in the cosmological enterprise, and some people wouldn't agree with this, but if you look back at Sloan Digital Sky Survey, classic, the original Sloan Digital Sky Survey, how did we measure 1 million redshifts? When we started taking data, everyone was like, well, how do we do 1 million redshifts? Like I had measured redshifts all in my graduate career, and I'd done it with a ruler. And the way we did it is we built a low-dimensional description of galaxies using a form of PCA. And that was a machine learning method, and that was absolutely critical to the execution of Sloan Digital Sky Survey 1. So I'm not saying that machine learning is out of the question. I'm just saying that if machine learning is happening in the interpretation part of the problem, in the part where we're talking about what is the physical measurement or the physical effect, we need things that we trust.
So you will reject every paper based on simulation-based inference?
If it uses an emulator, yes, I'm basically negative, yeah.
Okay. Good. That's a firm answer. I'll know if I write one of those papers to put you in that little box that says, do not
everyone be warned.
Nabila,
Yes,
what are your thoughts?
Thank you. So maybe I'll step back a bit and get back to the question that is asked for the debate. That is, what can machine learning do for next generation survey? And I think that if I were a referee of a paper claiming or presenting a discovery, whatever the type of study, whatever the type of method, whatever the type of approach, I think I would challenge it not that much in terms of precision, because I think that by now and in the future, precision will be very high. It's already high, but rather in terms of the accuracy of the result. And accuracy is basically whether the result is biased or not. And we have an example with the so-called H-naught tension of two exquisitely precise measurement of the same cosmological constant which disagree with several sigmas, and that we can't understand. So if I were the referee of such a paper, I think I would ask for explanations for precision on end-to-end simulations. And what I mean by end-to-end simulation is the process by which we have the end-to-end being explained and the simulation be explained. So simulation is not just the target probe, cosmological probe that we have, but this is the simulation of all the astrophysical contribution in the sky, dust being one of them, obviously, and not the only one, but definitely all the astrophysical contribution to a level that is reachable in terms of the sensitivity of the expected experiment. I mean, we cannot now use simple or very simple models. We really have to go into the details. So this is one part, the sky. I would ask for also simulations of the instrumental effect. And when I say instrumental effect, I don't mean selection functions or masks, because for me these are effective instrumental effects. But I'm really thinking of the low-level instrumental effect. Beam, being it chromatic, being it anisotropic across the sky, the shape, its transitionary aspect. The detectors, they have intrinsic noise, but they have also crosstalk. They have glitches. They have several aspects that they have remnants. I mean, they have many low-level aspects that are in fact what at the end will produce the measurement. So this is the simulation part. And then the end-to-end part of the end-to-end simulation is to basically run exactly the same data processing technique that will be run, or that has been run in this paper, on the data. From the data reduction, the low-level data reduction, to the production of the science usable or science available information, catalogs, maps, images, name it. All of this in order to trace in the highest fidelity possible the possible propagation of errors and propagation of biases from the sky and through the instrument itself. And just as a reminder, and I think I'm not mistaken by saying this, these end-to-end simulations have been the largest computational effort that took place for the Planck analysis, for example. By far, with respect to the scientific analysis, that is the cosmological parameter or the inference, etc., etc. And it was done for an instrument which was very simple, just a few million pixels of 5 arc-minute effective beam with 52 detectors. And we're now talking in the future, that is basically the paper that I'm looking at, to cases where you have billions of pixels, you have 100,000 of detectors in some cases. And I think that this is really maybe where machine learning can help. And I would turn, in fact, the question that is, what can machine learning do for your survey, to what can machine learning do to obtain or to produce fast and cheap, realistic simulations of the sky and of the low-level instrumental effect in order to run end-to-end simulations. And I think that we already have some indications that from the point of view of the sky part, maybe I'm optimistic, but I think that we may attain this goal, and we have heard about many approaches for the emulators, for the generators, etc., etc., and we will have this potentially knowledge. What I feel that we are lacking so far is digging into the gory, nasty issues of instruments using those very high performance techniques that we have, which are machine learning, and which I think will really help us characterizing much better the instrumental effect. And that's it. So I think that I would really need to be convinced from the point of view of going through each of the detail and translating those instrumental aspects systematic from the sky into something which can indeed be compressible at the end, but at least is encompassing the full complexity of the very complex instrument that we are building and that we're using now and that we will use even more in the future.
To go to the Planck example, something I think of where I can imagine, well, I think we certainly, or the Planck analysis team, would have certainly used machine learning, was one of the early challenges with the Planck data was the cosmic ray effects in the time stream were much bigger than expected. And it was a tremendous effort by the team involved. I think many people involved were actually in Paris at the time, looking at the TODs, fitting and characterizing the different kinds of cosmic ray events, how they were different classes, how they were identified and so on. And a particular exponential form was used because that's what, given the tools of the time, that's the best we could do. I think now we would actually be able to learn from the TODs, the cosmic ray effects, and clean the data in a much more
efficient way.
Actually, efficient way.
Yeah.
And both in terms of time and data.
Comment on that? Because I think that's a really great example, and I think I agree with Nabila completely that the instrument is where we should be using machine learning, because with the cosmic rays or with the instrument or sometimes with certain kinds of foregrounds, we actually don't care to deeply understand what's going on. You're not trying to build a map of the sources of those cosmic rays or the energy spectrum of those cosmic rays. That's exactly the kind of place where you want an effective model that explains the data very well. So that's a place where the ontology of machine learning is actually perfect for the scientific enterprise.
So yes and no, because for this specific example, in fact, the correlation of the cosmic rays that were hitting the Planck detector were associated with the solar activity. and the magnetosphere as well, and how far the cosmic rays were. So it's not that easy. At the end, it's not that easy. And what we have is data, and the data are not pure, perfect, fantastic. They're not just points. They are complicated. There are some, of course, cleaning. There's a lot of process in it. And I think that we need to at least make sure that the understanding of this and its translation into effective quantities, selection functions, space variations of noise, name it, are controlled and understood. And if I may continue, I think that there really is a hope to understand much better the simulation and the understanding of the sky. I mean, we have heard indeed yesterday about some caveats, the need for high resolution, the need for subgrid physics, etc. I mean, the population of people who are here are going to work on it. I hope that at some point there will be as many people digging into the nasty issues of the instruments. Maybe it's because I don't know, and maybe everything is under control, but I doubt it is the case. And my fellow colleagues who are analyzing the data from their raw signal to the end, I guess may agree with what I'm saying. So I'm going to stop to let Helena give her opinion on the question that was raised by David Spergel.
So coming back to the initial question, and allow me to bring it to my zone of comfort, which is galaxy evolution. What would I ask as a referee for? Sorry, I can't hear David. Yeah. Why would I ask as a referee if a new discovery was made using a machine learning technique? And I think there are two fundamental questions. What is your training sample, and what are your biases? If you're finding a new discovery, your training sample must be a simulation, because otherwise it would be in your training sample. And if it's in the simulations, then I totally agree with Nabila that we need to have very realistic simulations on the instrumental effect, and that is very evident. You usually need to use transfer learning or domain adaptation even when changing from one instrument to another, even at the same magnitude range or for the same task. But regarding the simulations for galaxy evolution are very complex. They need radiative transfer, stellar populations, so there are a lot of assumptions in there. And your result is going to be very biased on those assumptions. So I also think that machine learning is not the perfect tool for a very important claim. It is a very efficient tool for massive analysis of data, when, again, you don't need to have very accurate or a very certain measurement of your uncertainties, because that is something that I think the machine learning community is making an effort, but is having a very hard time to measure our uncertainties. And I will give you an example. When we try to measure the performance of merger detection algorithms, we usually use precision and recall, and for that, those metrics change depending on the fraction of mergers that you have in your sample. But that is exactly what we are trying to predict. So it's a never-ending story, and it's very difficult to give accurate measurements of uncertainties and therefore to reach the proper conclusions.
So let me now turn to David Weinberg for a few minutes. Since you spoke for a while, maybe a quick comment so we can get to some of the questions from the audience.
Okay. So I think the machine learning case is not fundamentally different from things we're already facing in cosmology, where we get an interestingly more precise result from going to nonlinear scales or including some new statistic or observable. So I think we already face these kinds of challenges in reviewing results. I think for me, the most, and also, in principle, we should have the same standards regardless of whether the result claimed is a 5 sigma, is W equals -1 or W equals -0.97 or W equals -1.03. although I agree with Hogg that it's hard to maintain the same level of rigor in examination in those three cases. But overall, the thing I most want for any paper that is presenting a conclusion about cosmological models against data is to pretty clearly show what goes wrong for a model that you claim to exclude. And I think lots of papers will show you the data and the best fit model. And something I try to figure out how to do in my papers and try to encourage others to do if I'm the referee is to show, here is a model that you claim to exclude at 3 sigma, show me where it fails. So, I write long referee reports, but I rarely reject papers. But Deep Thought's paper is one of the rare cases where I might actually reject it because of the answer that, I cannot show you in any way that you will be able to understand what goes wrong if you, sorry, this drill will stop in just a moment. I cannot show you what goes wrong if I set W equal to -1. So really I want a demonstration of here's how I can't reproduce the data for a result I claim to exclude, whether that excluded result is a conventional one or unconventional one, and then running through, here are the other possible explanations, and here's why we don't think it's this, here's why we don't think it's this, here's why we don't think it's this, and those possible explanations might be astrophysics, and those possible explanations might be instrumental, but if there's a reasonable case for rejecting them, then I would accept the paper, but I would, I think part of what always saves us in astronomy, or at least has to date, is our data keep getting better. So if you have, a 4 sigma result, then, a few years later, it better be a 10 sigma result, or else it was probably wrong. So I'll stop there.
Yeah. So, before turning to questions from the audience, I just want to give my own response, which I think is a little different. Some of this is actually based on, I will now confess, being the referee on the parameters paper for Planck several times. And that was, a very important paper that one wanted to make sure got right. It was a very complex set of steps in the analysis and wanted to make sure things like the way the cosmic rays were removed didn't affect the data. And I think one of the great things about the Planck data, and we did the same thing earlier with WMAP, was all the data was public and all the code was public and a lot of the details were public. So one was able to go in and check parts of it and see what was going on. And we found in the initial data that the different detectors sitting in the same bolometer were actually correlated. Right, and learn to only use cross correlations. Right, this is something I've learned in my analysis of CMB is do never use autos, just use crosses, and you get more reliable results. But the fact that as an informed referee, you could actually go see open code and open data, and I think that's something I would want to insist on in this from Deep Thought. That a lot of the pieces were testable that way. And the other, and this is...
No, go ahead.
Yeah, and this is something, now based on my experience as foundation president, kind of looking across lots of different fields, is what I think is a measure of a healthy relation between theory and experiment or theory and observation is an important paper should suggest new measurements, right? So the outcome of this Deep Thought paper should not just be W equals minus, 1.05 or whatever the value was, but that given that value, we saw that the temperature of the ICM was really pretty high, right? And this comes to mind as one of the things I've learned from the simulation is the fact that if we could get a good measure of the global Y distortion, this would be a really valuable measurement for understanding the amplitude of galaxy formation feedback. And that suggests a new balloon experiment to do, the spectrum measurement has not improved since Kobe, right? And that's something we should do better. And there's, there could be a measurement on the Lyman alpha forest, or, for galaxy observations, I think the submillimeter is so important that that there's a surprising results suggesting some new measurement at other wavelengths and other ways, to me is sort of an important part of our scientific process. And we should be asking, if you can't tell us exactly what you're doing, tell us how you should be tested by future measurements, particularly those that we haven't taken before.
Yeah, I agree with that. One very interesting thing, David, as you know, I agree infinitely with the point that everything should be open, and we've dedicated a lot of resources to that at CCA. I do think that one of the dangers of very large machine learning models is that they will become impossible for normals to run. It's already, it's very hard to reproduce AlphaFold. Some of these models are very big.
Yeah, so we're just about to, there's a pledge that's circulating around a number of major companies, universities, and organizations that will come out in a week or two that basically says all codes, all weights should be open. It's, opposed to this notion that this is a powerful technology that must be kept hidden. And, I think...
Agree.
But I think that...
I think that's...
Oh, sorry, David. I fully agree with this, but I think that it also needs some ethical frame, let's say, in the sense that making data public is not just any data. It's data that people can use. So it's data, it's usable data, usable codes, and those are really the requirements, because I mean there have been in the past at least several attempts to publishing data or making them public in other domains. I mean not specifically in cosmology, but at the end the data are not used. Cannot be used at all. They're not intercalibrated. They're not usable at all. But still, I mean, you ticked the, I mean, people tick it, and okay, my data are public, and at the end, nobody can use them. So there really is some code of conduct of open data, and open codes, and that are in fact already existing, but that need to be enforced. I think so.
And if I may add to this, there's also the complexity of using different codes, different programs, that how all these, the different versions change very fast, and then you publish a code and 2 years is obsolete. So it makes it's a big effort from us that we already have a lot of work to do to make it usable, user-friendly, and then in 2 years' time, it's an obsolete code. So I agree that we have to be transparent, but I don't think it has to be compulsory.
Or at least if it is compulsory, then it is clear that there are resources which are associated to this effort and which are additional resources, I think, if it is compulsory.
And I think I agree, but I think it's going to require both resources, but also recognition by the community that people who develop and maintain those kinds of codes are incredibly valuable to the scientific enterprise. And I think this is going to be particularly true as we have more and more complex codes and calculations involved with things like machine learning. So we have some questions here. So I'm going to ask Paco to raise them, and then I think perhaps the best format would be to ask the panelists to raise their hand if they want to weigh in on it. I don't think we need to have all of us comment on it, but if any of you have a response or a thought to the question, please raise your hand. So Paco.
Yeah, there are a few questions in Slack, but maybe we can start with people here. I don't know if anyone, please go.
You hear me? I'm really happy that David Spergel thought that the cosmic ray stuff from Planck was important, because that's about the least cited of all the Planck papers. It's the cosmic ray paper. But to be more serious, the effort that was put into that by Guillaume Patinchon and others, it's very unclear how you would do that with machine learning. I mean, maybe at the end of the process, you could throw it at some machine, but the work that was required to do that was ongoing and developed over years. It was completely unclear at the start of that process how you would do it, and therefore it just required people and labor to figure out how to and people go into the lab to do extra tests and all sorts of things. So I don't think that's a good example of a machine learning.
Well, I think it's just ability to represent complex functions. If I remember the paper, it was fit with there were functional forms assumed for the 3 types of cosmic ray events. And those functional forms were ad hoc. They were fits. And machine learning, neural nets allow more generalized functional fits. So I think that becomes a tool that, you just definitely don't throw it at the computer.
Yeah.
But I think it becomes a tool that clever, hardworking people who understand the experiment have a more powerful functional representation that they can use for that would be my, when I think about that, I remember reading that, since I can remember the paper still, the exponential forms worried me because they were ad hoc, but they seemed to me to be absolutely the best thing you could do, and I couldn't think of anything better.
But it was all developed by hard graft by a few humans before you could go anywhere near a computer.
Well, but I'm sure they were using a computer.
I don't think that the question is to replace the humans that did the work by machine learning, but just to complement at some point, as you were saying, Doug. Maybe I don't know whether it's at the end or not at the end. And for Planck, it was different. I mean, we had just 52 bolometers or detectors to go through. But imagine a next mission with a few thousand or a few tens of thousand detectors. Then you could really use this as a database, since the start, and enrich it. And then so you could think of it. It's just an additional tool. It's not really replacing people, of course. I don't believe that machines will replace people.
I mean,
I hope I'm true.
AlphaFold came up a minute ago, and if you look at AlphaFold, that paper has, I don't know, more than many authors, dozens of authors, maybe hundreds of authors, all of whom, and many people aren't authors, and they're paid very well at DeepMind. That is not a small engineering effort. And so, it's impressive that they did so well with the protein folding, but actually the total economic load is very high. And so I think I'm agreeing with this question that there's a lot of human thought that goes into these things. It's not like you just throw machine learning at it.
And if I may comment on that, I think the fact that we, the astronomers, are the ones using the machine learning is the right way. There was a suggestion in a conference I was last week of having this institute of machine learning where you will give your problem to some software engineer and will make the perfect code for you. But I think that cannot be the case because we are the ones who understand the problem and the bias of our results. And humans will, I hope also that humans won't be replaced by machines because we are the ones creating the problems, understanding the errors of our own solutions and improving our solutions. And if you don't really understand what is the problem that you want to solve, it's very difficult to solve it properly.
So we turn some more questions to the audience booth.
Can you hear me okay?
Yeah.
I wanted to speak up in defense of deep learning a little bit. When people worry about the black box thing, I ask them, have you seen a bispectrum lately? We are already in the range.
Yes.
We are going from, a data vector that's hundreds of elements to thousands. In weak lensing anyway, they're all like 2 sigma points. Good luck trying to develop physical intuition with that. I guess my point is that we more or less rely on simulations of either the physics or the detectors to understand different effects. It's not ideal. I would love analytical ways to do it, but we typically rely on simulations. So if that's the case, then it's not a huge leap to go from a bispectrum prediction to a deep learning analysis. Not ideal, but I think that is the world we live in.
I don't agree with that point of view at all, because the bispectrum is being computed by a piece of code that has internals that are very interpretable. You can look and you can ask, is the stress tensor conserved inside that? You can do a lot of work on the simulation and understand where that bispectrum estimate is coming from. So there's uninterpretability and there's uninterpretability. And I think it's true that some observables are very large observables, but at least we're confident that they've been computed in a way that's consistent with our beliefs about the physical world.
Yeah, I agree with you, David.
We have a question in Paris from Licia.
I actually had a comment that, in the sense that I don't agree that the bispectrum is not interpretable. Of course, you have to learn to love it and understand it. It doesn't happen overnight. But in general, I agree that there are parts of the data vector or the compressed statistics or summary statistics that are less transparent than others, but then it's the effort of convincing the referee how that summary statistic responds to a change in physics, which is exactly what you are after. And so you would have to do the same for your machine learning. And we have heard some of the talk when this actually happened, I mean, even connected to the Fisher information matrix. So we go back to even earlier time, even before MCMCs. So yeah, just...
I'll just make a brief response to the distinctions you both made. I think the issue really is compute often. You can do a lot of the learning and experimentation with a deep learning black box also, if you're able to run thousands of simulations.
We have another comment here, Luisa.
Yes, hi. Yes, I was interested to see David Hogg's kind of grand claim about interpretability being a failure when, you know, there's a whole community of us not just working on interpretability tools, but actually trying to use them to make scientific progress, and not to mention, you know, the computer science community working on explainable AI as well. So I think, you know, it can be a bit damaging in some sense to just make an abstract claim about interpretability without being specific about what you mean and in what context. And then I think I was even more a bit disappointed to see that, you know, somehow results coming from machine learning methods, you know, the same rules don't apply to other methods, right? I mean, we're looking for robustness, we're looking, as Nabila was saying, explanations for results, but I don't see why, you know, machine learning results have to be a priori excluded because of a grand claim of failure.
I mean, I would say, so I agree that lots of people are working on interpretability, and I do think that there are interpretability successes in a certain sense, but I think the successes are very much like treating the machine learning method as an object of study rather than like latent space interpretability. Even a linear regression, the weights are not interpretable and they're very unstable. Once the number of features gets large, the weights become extremely unstable with respect to the training set. So at least in physics, I don't know of any case where a machine learning model was run, and at the end of the day, the interpretation of that machine learning model led to an insight about physics. But if I'm wrong, I'm happy to be corrected.
David, we have another question here, or whether you want to go back to New York.
Respond on that one?
Yeah, no.
I think, so I agree with the point that you want the same standards for machine learning as for other things. And as I said, I already think, you know, this question is not fundamentally different from, okay, you're using scales in the nonlinear regime and halo occupation models or baryonification models or anything else. I think and so we've had this sort of vague, well, this, or the unspecific, this result relies on machine learning, but it really, it matters how. I think the place where, to me, I'm still most worried about the black box effect is things at the level of field level inference, because I can see that field level inference is in principle the right way to get the most information out of the data, but by resisting summary statistics, it's very hard to do the test of, okay, I take some counterfactual assumption, lambda CDM or some other value of W, and you can see where things go wrong. So I really do care about this. If you make a claim for parameter values in some range, then you have to be able to show why models and data disagree when you go outside of that range, and you have to be able to show it in an intelligible way. And that, I think, can be a challenge for field-based inference. I don't think it's a problem for simulation-based inference in general, but I think it requires some summaries of the data.
So let's take one more question from Paris, and then we'll go on the web and then return to some questions here in New York.
Please state your name.
Hello, my name is Ethan. I'm from EPFL. I guess this was what I think David was saying about confirmation bias. I think I'm just trying to, maybe I misinterpreted it, but is it not just, I guess, Bayes' theorem where if deep thought made its extraordinary claim that it was -1, does that not then require extraordinary evidence? So if it doesn't provide this evidence, we can reject it based on Bayes' theorem. And if it provided an answer that we expected, we don't need as much evidence. So is that more Bayes' theorem rather than confirmation bias?
That's a very nice question. That's a complicated, I think there's a smooth transition from relying on your priors to confirmation bias, and I don't know, somehow in the community I'm seen as a Bayesian, but actually I'm very much old school. I would like to see the data speak, and my only point is that part of the point of astronomy is to discover things we're not expecting, and part of the point of cosmology is to break our beliefs about the world, about the cosmological model, and so. But yes, you can see it through a Bayesian perspective. But of course, if you take a very strong perspective in that direction, you'll never check anything.
Thank you.
Other comments from the panelists in defense of Reverend Bayes?
Well, maybe one could say that extraordinary claims require extraordinary evidence, but ordinary claims require at least ordinary evidence.
No, talking about biases, if you train a model that has learned that the most massive and reddest galaxies are ellipticals, you will never discover interesting objects like red spirals, right? So you really have to be careful that your model is not learning the most basic correlation between your data, that is really gaining the details. You really want to understand the details if you want to learn new physics. And that will be the case, for example, if we train a very simple model, the machine learning would have called me David and would have guessed my name with a 30% accuracy.
It's not a Manel, it's a Davidal.
I think this point about what's in the training data is a very important one. And I think it's something that's I've seen forgotten in some astronomical papers where people say that they're learning from the simulations and don't think about the fact that a set of simulations imposes a prior. I just saw in the news that General Motors is abandoning pretty much its investment in self-driving cars. And what has been the challenge for self-driving cars is you've got to get enough training data to cover the space of all potential experiences that you will encounter on the road. And I think one of the things that, to be mindful of is to make sure that we cover the space in ways in which we don't impose strong priors that prevent, the kind of discovery that Helena was talking about. Okay, we have some questions on the web.
So there is a question from Flor, I guess for David Hogg. So do you see AI only as a co-pilot for astronomers?
No, I think that, I do think there's tons of rules. I think the fundamental question, which is what I kind of posed on one of those random slides, is that you want to find places where you can use a model you don't trust. And where can you use a model you don't trust? So I don't think it's just Copilot. I think there really are places in the system where we just don't care that much about the underlying physics. And maybe I'll offend Spergel here by saying that, like, if you're trying to look at primary CMB, there's these foregrounds, and at some level, you don't really care what causes the foregrounds if you're trying to look at the primary CMB. And so there's a role for machine learning in there where I'm perfectly happy, because you might say, well, it's not doing the right things. It's not doing something that we can understand. I mean, if it gets rid of the foregrounds, I'm cool with it. So I do think it has to pass tests, it has to do things, but I wouldn't say just as a co-pilot. I would just say you want to position it in the parts of the problem that you're not trying to deeply understand.
Of course you do care about what's causing the foregrounds. I mean, you definitely do, because the distribution of the foregrounds in the sky will not look the same depending on the way it has been formed. Their properties will not be the same, their characteristic will not be the same, and you will not be able to do your cosmology properly. So you really do. Or you can tell me, I'll marginalize, okay? You marginalize and you marginalize and you marginalize. But I mean, is this a way to have, no. And I leave David Spergel continue, maybe, arguing that you do.
But I like what Nabila is saying, because you're definitely going to believe more a foreground model that has a physical structure you believe. But frankly, if it was very complicated and those relationships were very hard to see, I think we could live with an uninterpretable model.
I think that you can live with a knowledge of the foreground which is at the level of the quality of your data, okay? And that's the big problem, because you have to push your physical models to the level of your data, and a little bit better, of course, to make sure that you can indeed disentangle between what is the physical assumptions and the data. Because, I mean, of course, you could say, well, it's a power law, and that's there's no problem, but it's not the case. So I agree with you. Maybe we don't care about the physics of the foregrounds, which I would agree somehow. I mean, it's not my main interest, but we care about the. It's not a foreground. The SD is very important.
Lensing?
Lensing? No, more seriously, I mean, we may not care about it from the point of view of understanding really the underlying physical models and grand things about the foregrounds. But we definitely need to understand them, and to understand precisely enough to the quality of the data, I think. Well, me, with personal opinion.
Good. I agree with that.
When I heard about Copilot, I just came to mind this image of this bumper sticker that used to be popular. People would drive with a bumper sticker that said, "God is my Copilot." It always worried me that they were trusting in God to keep them on the road. But I guess today we would have people with cars that say, Elon Musk is my co-pilot. And one should worry about how much you want to trust someone who's deeply in Elon Musk.
That, machine learning is bringing us a bunch, it's not just co-pilot, but it's bringing us a bunch of new tools to attack problems, which in some cases we could attack in other ways. In some cases we couldn't computationally feasibly do it. I think that if machine learning has as big an impact on astrophysics as the fast Fourier transform, that will be a huge success,
yes,
right? And we should count that as a big win. And, you know, I think we're currently, and I think it is possible that the importance of machine learning will exceed that of the fast Fourier transform, and it's possible that it won't, you know, quite rise to the level of fast Fourier transform. But I'm, at the moment at least, sort of thinking of it in that category.
Yeah, I actually agree with Dave Weinberg. I think machine learning will turn out to be as important as something like PDEs, that there'll be a set of tools because of its ability to represent functions in high dimensional spaces that will let us do things we couldn't do before. And I sometimes think in interpretability, I think of Isaac Newton, who invented this thing called calculus, but he knew that people wouldn't trust it. So he derived his results using calculus, and if you look at Principia, it's all done with geometry, because geometry was the summary statistics of its day, kind of understood by people, and they felt comfortable with it. But he really got his results with calculus. And of course, that's, you know, now it seems crazy to say people didn't trust calculus. But it took, in a way, a generation of mathematicians, several generations, to develop the fundamental understanding of how functions work, so you can understand, you know, Fourier transforms and calculus. And I suspect we'll need a much more profound understanding of the mathematics of machine learning to make, you know, before we truly can get its true power.
I support that strongly, and actually the little bit of machine learning I'm doing right now is very mathematical, because I do think that if we can control a little bit more of the mathematical properties like symmetry obeying and conservation laws and things like that, I do think that we will get more trust. You know, I'm very focused on trust, and maybe we can improve trust by just understanding it more from a mathematical perspective. And of course, a lot of people working on that. That is a very, very rich and exciting field right now.
I have a question for you. Do you think that because machine learning is moving so fast, it's evolving so fast, that it's difficult to keep update, it makes doubts on how reliable the new models are? Do you think this speed is going to saturate, and then we're going to find like the optimal tools, and we will establish our principia for machine learning?
I hope that wasn't directed at me, because
it's for the audience.
It's for the audience, yeah. So, the audience, here or there.
It's weird when the panelist asks.
Please shoot questions.
I'm not sure about Principia tools, but I think it's interesting the historical parallel that David Weinberg opened, and we spoke much on the machine learning half in that parallel, but the other half was also the big simulation with all those big GPUs. And in that, it is non-interpretable in the sense that, much like the bispectrum, we do know all the pieces involved, but we don't know why it comes out the way it does in some fundamental way. We don't know why Illustrious TNG and Horizon AGN and Simbra give significantly different answers, even though we know all the pieces, much like a deep network. But we've come to trust them, I think, because we've spent 40 years developing some tools to do some checks, in part, and in part because we have to. It's become just the necessary part of doing science. And I wonder if machine learning will go in a similar direction, where it's a combination of explainability being developed, and we just have to. So I really applaud the people, like I think it was Lisa, who work on explainability now. And I think as someone who builds big models in astronomy, there's not a good incentive structure right now to do the kind of checks that you talked about for Planck, and maybe even in Planck. It's a very poorly cited paper.
Thoughts and comments besides my desire to defend the bispectrum as Lisa did, as interpretable and with analytical interpolation.
So I think with regard to interpretability of simulations, I would say, you know, when I started working in numerical cosmology, there was definitely a, you know, fairly fairly strong view among theorists, not universal, but that simulations were a black box and basically analytic calculations were the only way to actually understand things. And I've always argued that there's a lot you can get a lot of intuition from simulations by changing the inputs and seeing how the results change. That there's a lot of internal things you can do, and that in some cases, at least, I find the analytic results more opaque than the numerical results. So I do think, at least within simulations, it's this really looking systematically at how inputs change outputs that's given us intuition, but also in terms of robustness, it's being able to do the calculations with different codes done by different groups, different initial conditions, that has given us a sense of, all right, here's where they're reliable and here's where they're not. So I think we are seeing some of those same things with machine learning tools, but that is what both of those methods will be important in getting machine learning to be as valuable a tool as numerical simulations.
I mean, people haven't mentioned adversarial attacks, but adversarial attacks also fall into this interesting category.
No,
I was about to say, provided we struggle against our biases and give those new methods the chance and indeed the same rules in terms of robustness, traceability, etc. And that's really a sociological effort that we have to make. I mean, personally, I find it super exciting to have those new methodologies. I mean, simulation-based inference. Who would think about it? And I think it's necessary because the complexity of the data and the complexity of the models that are needed to explain the data needs it. The field inference being capable of identifying systematics. I mean, this is really superb in terms of tools, okay? Tools, not replacement.
Yeah, I just wanted to follow up to say I totally agree. It's also like to install a culture of like making sure you understand what's going on. And I just wanted to remind people that actually in DES, we could have said we detected W equal -1 because when we unblinded, that's what happened. But that's not what we did. We went back, waited for another galaxy catalog, rejected data. So we have to be absolutely ready to do that. And I want to remind that when we work with raw data, we actually don't want that much to detect new physics because it would be so like such a polemic thing. Like, so for instance, for test of gravity, we remove 50% of our data. So that's the reality of actually looking at data right now. And I think that will be the case as well for SBI. So these types of robustness test, validation of scale cuts, or like the choices you make is most of the work actually right now, and probably will be very important. And I think in general, surveys will have to decide themselves what are the steps they want to check, like what box they want to tick, and if they don't manage to solve that, like what do they have to do? Like if they see W equal -1, different from -1, what do they do next?
Weinberg, you have your hand raised. You want to comment on this?
I think that, at least in my understanding, it's when we get to simulation-based inference, that's where the questions of adequacy of the training data become the most, the most important, because that's, I do think simulation-based inference is a great tool. And allows us to do things that we otherwise wouldn't be able to do. But it is the place where there's perhaps the biggest risk of you reach a conclusion because there was a piece of either physics systematics or instrumental systematics or something else that you just were not including in your training.
No, fully agreed. It is a superb tool, provided the level of simulation is indeed the necessary one and includes the major effect. Definitely, I mean, I fully agree. Yeah.
And it's not all, this is the case not only for machine learning, it's the case for any estimate we do,
exactly,
right? For example, if you want to estimate galaxy ages, you need to fit a template of stellar populations, and for that you need to do assumptions. Is it single stellar population, the metallicities, then if you assume mergers, and then there's something which is even more important, you have degeneracies. What happens if you have two sets of data that produce the same observations? And sometimes we are trying to ask machine learning to give us the right answer when it's impossible because it's totally degenerate. So I think what we need to do is to understand the limitations of machine learning and be clear on the table. I'm afraid that there's an explosion of machine learning. There's a lot of papers, a lot of people working on that. And therefore, we need to be very critical with results which are not very clearly explained, because that will cause a bad fame for our methodology, right? So we, as referees, we need to be very critical about the assumptions and the results that the papers are presenting. But it's the same with more classical approaches.
Yeah. I mean, I think one of the things that's been essential in sort of classical approaches has been null tests. Right, and there's lots of null tests one does on the data to show that there aren't things in the data that you didn't expect, and there aren't surprises, and there's clear tests. I think in principle, simulation-based inference should enable far more null tests because you could model things forward. It really should be a tool that lets us do more consistency checks on the data. But I think it requires, and this just goes back to some of the almost really ethical themes that people have brought up, is that we have to, if machine learning is a powerful tool, with powerful tools we have to hold ourselves to even higher standards of testing and consistency.
By the way, that is an interesting point. You use the word ethical, and one of the things that's interesting here is that a cosmology could be almost like a sandbox to think about much bigger issues in machine intelligence that are in play. And so I think it is kind of interesting that we're struggling with these things, because solutions we find might be like little tiny babies of solutions that could have much bigger applications.
Weinberg.
One thing I'd like to come back to as a question for either panel or audience is, this goes back to something Brice said in his opening remarks, that part of the potential power of machine learning techniques is the ability to deal with complexity, and I agree with that statement. I do find myself feeling that, with regard to a cosmological conclusion, I'm not sure I'm willing to, in the end, accept complexity as being, part of the answer that convinces me something about W or modified gravity or something else, and that, if the answer ends up depending on spiral structure or ratios of ellipticals to spirals, I might just in the end not believe it. So on the one hand, I think it is true that machine learning gives us these tools for dealing with complexity, but a lot of what we have been saying so far is that in the end, we actually want simple answers that we can, filter reasonably easily ourselves. But I'm interested in any reactions to that. And people would say, no, we could take a fundamental conclusion based on a pretty complex interpretation of the data.
So you would stop the analysis to the linear regime?
No, I'm a big fan of the nonlinear regime, so I agree. I'm willing to deal with some level of complexity, and the question is, but would I allow it to go to, the level of complexity where I felt I couldn't actually understand it without a machine? I'm not sure.
Okay. So let's ignore machines for a moment. There's lots of papers that come out that make the following claim. James Webb's detection of high redshift galaxies, black holes, whatever, undermines lambda CDM. Makes the front page of papers, gets issued by, right? Now, my faith in our understanding of UV emission by stars and at redshift of 10 does not require any machine learning. But yeah, I don't know. I mean, there are lots of things where people evoke highly nonlinear physics to make very strong claims.
And you didn't believe the result?
Yeah. But it doesn't stop lots of other people from believing it and holding conferences.
Yeah, I totally agree with that, and that was my point before, right? Like, we are asking machine learning to be sometimes more accurate or more precise, and many of the tools that we use, we as astronomers have so many underlying assumptions. I really like your introduction ordering mathematicians, physicists, and astronomers. So I think machine learning may overpass us, so we have to be careful.
Ben has a remark as well.
Yeah, this is fascinating, but there are different kinds of complexity. I mean, there's complexity that emerges from simple underlying physics. So, for example, gravity, we have a nonlinear regime in gravity, and until a few years ago, I think the jury was out how far into, how far we could actually understand that, how much could we actually really understand the details of the small-scale nonlinear gravitational physics. I mean, but there are simple underlying rules, and I think over the last few years, what has emerged is that that problem can be solved either with deep learning techniques or with other techniques. But there are now some results showing that we can essentially invert gravitational evolution deep into the nonlinear regime all the way back to the initial conditions. So that's the type of complexity that we can address, and that doesn't, once you've done it, the moment you've done it, it doesn't seem so impressive anymore, because there are other even more complicated and even more complex issues to be solved. But let's also recognize the fact that these techniques have have allowed us to make significant advances.
So we're getting to the end of our time. So I want to turn to the panelists and ask if people have any final remarks before we close. Start in Paris.
What's the question, sorry? Yeah,
final remarks.
Final remarks. Things you want to say before we end.
Yeah, go ahead, please.
Final remark.
Let me see.
Well, as I said, I think it's really an exciting period. We have great data, and we have great brains, and we have new tools. I'll get back to what I was saying in the beginning. My wish, my dream, would be that there are almost equal interest or activities to apply those techniques to the not that sexy, fantastic, shiny topics that are the determination of cosmological parameter or finding, I don't know, which kind of new physics, but really into understanding complicated rather than complex, complicated matters like instruments, like baryon physics, in order to enrich our understanding of both the measurement techniques and the measurement itself, I mean the measure, the act of measuring, and the underlying sky.
For me, I think we need to step back and make the right questions, right? If we want to find the right answers, we need to answer ourselves the right questions. And I have the feeling that because of the boost and the explosion of machine learning and everybody getting funds if you do the magical word, we are looking for problems that can be solved with machine learning, like classification. Well, this data is perfect for applying a machine learning. But okay, once you've done that, what is the physics that you want to understand? What is the astronomical problem that you want to solve with that? So let's try to figure out what are our open questions. And if machine learning is the right tool to answer them, let's use them, but don't forget traditional tools that we have on hand.
Hogg?
I've successfully come off as the hater in this panel, and I'm happy to take that role. But in fact, a lot of my work is on machine learning and has been for a long time. I do think that machine learning is absolutely essential in the toolkit going forward. We need it for computational scaling. That's why simulation-based inference is based on it. We need it also for training the students, and the students that come to us to work in astrophysics, they expect to be trained in machine learning techniques, and I think that's critical. So I think the most important thing here is trust, and that's one of the reasons I've been working on mathematical aspects of machine learning and provable aspects of machine learning and introducing symmetries and things like that. I think the way forward is to make machine learning models that we are better able to trust and control and see as components of a rigorous physical model.
Weinberg?
So I think in cosmology, as in most areas of astronomy, we benefit from the fact that data get better pretty dramatically over time. And so, any interesting result, usually over time it becomes clear that it's either correct or not. So, for instance, the supernova cosmology evidence for acceleration, was confirmed by lots of other things pretty quickly. So I do think that will, protect us against going anywhere far wrong. As working scientists, we're always trying to place bets with our time. And so, when we look at 2 sigma, 3 sigma, 4 sigma results, we have a big stake in deciding whether this is important, this is believable enough that we should actually spend time on it or not. So it's somewhat different for sort of people working in the field versus the overall progress of science. The last thing I was going to say, I'm also very excited about these techniques. I do think that there's always some people who are quite cautious, some people who are ready to go out and make big claims, some people who love to work on the technical bits, some people who only care about the big theoretical interpretation. I do think as a community we are way better off having people with all those different attitudes. And we waste our time if we're sort of criticizing some people for being too cautious or some people for being too adventurous or whatever. Collectively, it is way better to have a community of people who actually have different attitudes about how to do the science.
So let me just conclude by saying I think machine learning has a lot for astrophysics, but astrophysics also, for that all lot of the reasons we talked about, offers a lot to machine learning, right? We're operating on problems that are complex enough that the tools are important, but interpretable enough, and there's new enough data, new enough ways of doing things. I think it's a good place to learn the limitations and how to use the tools. So I think we're all lucky to be here at an exciting moment, in an exciting field, and thank all the participants on the panel and the audience for a fun discussion. Thank you all.
Thank you.